So in mathematics, we have something called a set. A set is basically a collection of things. This is a very informal way of defining it. It's a very old definition. Okay, a set of things, a collection of things. So if I have like maybe four numbers, this is a set of four numbers. If I have, I don't know, letters like A, B, D, F. Okay, these are a set of four letters. Okay, and the thing is, sets are pretty boring if you think of it like this. You can use them in math sometimes, like the set of, numbers between 1 and 10. 10, that's 10 stuff, that's 10 things. It's pretty boring. However, when you start talking about infinitely big sets, that's when it gets interesting. Okay, so J.R. Cantor, the guy who kind of started the whole set theory business, he was thinking, could I have a set with infinitely many elements? And could two infinitely big sets be equal in size? Or maybe I could have two that, are not equal in size. One infinitely big set, weirdly, may be bigger than another infinitely big set, which is a bit crazy, right? How can you have this kind of situation? They're both infinity. How can you have one that's bigger than the other? Well, Cantor defined the equivalence of like size, the same size, through one-to-one correlations, essentially. If I had this set that's like 1, 2, 3, 4, had four elements, and it had also A, B, C, D, another four elements, to make sure, to know that these two are equal in, the same number of elements, I just need a one-to-one correlation between all the elements. There, boom, same number of elements, done. So this is pretty boring because you can just count the elements when it comes to like a finite set of finite members. But what if you had something like an infinite set, like the set of natural numbers? Okay, so 1, 2, 3, 4, 5, 6. Now let's look at the set of natural numbers with 0. Okay, 0, 1, 2, 3, 4, 5, 6. Which one do you think is bigger? Well, intuitively, you'd think this is bigger, right? This is everything, has all the same exact values, but with 0 in it. So it must have more, right? It's like this infinity plus 1, okay? But you can still make a one-to-one correlation, and you're not going to have, one more term on this set, because there's always going to be infinitely more. It keeps going on for infinity. Both sets go on for infinity. So technically, this 6 has a one-to-one correlation with the 7, and then so on, so on, so on. Thus, despite, your intuition telling you that this is bigger, it still is equal in size, which is kind of weird, right? It's a bit weird. Infinity is weird like that. And I'll show you another cool example. Let's say I have, 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4. Now, this set of positive and negative numbers, okay, versus the set of just positive numbers, 1, 2, 3, 4, okay, you'd think, because this set is bigger and it contains this set, okay, you would expect that this would be bigger, right? This would be bigger. Well, if I were to draw a zigzag line like this, lining, catching all the numbers as I go, and this would go on to like minus 5 and 5 and so on, so on, you realize if I also draw a line connecting all these, the first number that the line touches correlates with the first number the line touches here. First number the line touches here correlates with the first number the line touches here. This correlates with this correlates with this, and so on and so on and so on. Thus, despite your intuition telling you that this must be twice as big as this, it's the same number of elements. It's weird, right? Infinity is that weird. Now, what about the set of real numbers? Real numbers have no real inherent pattern. They can go like so weirdly like this, or they can go like 2.3465. They're not repeating, okay? Real numbers can go like this. You can have normal real numbers like 3, or you can have like 3.333. That's a rational number. But irrational numbers like these that have no pattern to it, it's a bit weird. So can you make a one-to-one correspondence? Okay, so let's say all of the sets I showed you just now, the set of negative numbers and integers, the set of just integers, the set of integers with 0, all of those, okay, I'm going to call them, they're all the same size, and they're all basically the same number of elements, okay? And, I'm just going to call them, okay, that's a very weird looking N. Okay, so this is basically N, the set of natural numbers, okay? And it's the same as the set of all integers, including negative numbers, same as all the set of all fractions, it's the set of all negative numbers plus integers, the set of all integers with 0. It's the exact same size. They're all the same size. But what about R? You know, the set of all real numbers, which includes n, but we saw earlier, just because it includes one set is a subset of another set, you know, one set is inside another set, doesn't mean one is bigger, okay? One can still be equal in size, have the same number of elements. So do these have the same number of elements? Do these have the same, you know, the same number of members? Can we make a one-to-one correlation? Now, let's try, okay? Let's try. So represent the, you know, the regular normal natural numbers, 1, 2, 3, 4, 5, so on, so on. Now, I'm going to make a bunch of random real numbers, okay? Random real numbers. So let's say, I don't know, this is 1.010101. So I'm just going to make a series of randomly weird numbers. So, a bunch of random numbers, and let's say these go on for infinity. So, if we're gonna, let's just assume there is a one-to-one correlation. Okay, let's say that there is a one-to-one correlation. So, I can't write all the possible different in order, all the different real numbers in order, because there's like it's like this infinity is different. Okay, I can't just go like 1.1, 1.01, 1.0001. I'm gonna be stuck at just the ones. So I just have this random sequence. While over here it's in proper sequence. Now, if all of these are the same number of elements on both sides for the natural numbers and real numbers, that means, and they correlate 1 to 1, it is going to be impossible to make a new real number that is not on this infinite list. It's impossible, okay? So, let's say I can do that. That means the whole idea that they're equally in the same number of elements is going to be wrong, right? Well, how can I do that? Now, let's take this first number and let's change it. So it's the exact same number. It's like I'm just gonna change it to 2, something else that's not the same as 1. I'll take the second number. So I make a new number, okay? And the first digit is 2. Second digit, change 0 to 1. Third digit, change 5 to 6. I'm increasing everything by 1, but it doesn't matter what's, you know, the pattern. I'll change this, you know, I'll change this 2 to 3. I'll change this 8 to 9. And my new number is going to be made of these diagonals, but different to all these different numbers that I circled. This number is not the same as here, because the first number is different. It's not the same as here, because the second number is different to the second number here. It's not the same as this number, not the same as this number. It's not the same as any of the numbers that will appear on this infinite list. I can make a new number just by taking the diagonals and changing them by 1. And I made a new number that doesn't exist on the infinite list. It's a bit wild. It's an infinitely big list, and I can still make a new number that does not coincide with any of the numbers that can appear here. Which means the set of real numbers, which has really unpredictable patterns to the digits, is bigger than the set of natural numbers. And that's when we learn that some infinities can be bigger than other infinities. It's weird. Infinity is a weird concept. Infinity is not normal like finite numbers. Somehow, the infinity of real numbers, you know, is somehow bigger than the infinity of natural numbers. It's such a strange phenomenon, but if you look into set theory, it gets weirder. There's stuff that's even bigger than, you know, there's a lot of different interesting concepts. You can watch Vsauce's video about it, about the nature of how weird infinity is and how it can go even further than this. But this is kind of an introductory to how weird infinity is and how infinities can be different. And this has been the proof that J.R. Cantor gave, that, you know, one set of numbers can be bigger than another set of numbers, even though they're both infinite. So yeah, that's basically it.